Hi, welcome to MooMooMath. Today we are going to do the second lesson in a series. This is on reviewing unit vectors and then how to write a vector in component form. That's review. And then we're going to do a little bit more with magnitude and direction. So let's start with a warm-up. Write the unit vector that has the same direction as vector v. So vector v is the vector, and I'm just going to sketch it. It's in standard form, so standard position, I should say, at -3, +4. So here's my sketch. There's the initial point is at the origin. The terminal point is at the point -3, +4. Now, to find the unit vector, I first have to find the magnitude. Well, I hope you recognize this as a 3, 4, 5 right triangle. So that means my magnitude is 5. So I'm just going to take 1/5, so 1 over the magnitude, times the vector itself. And the vector is -3, 4, and if I distribute that -1/5 in as a scalar multiple, I will get -3/5 as my horizontal direction and +4/5 as my vertical direction. So I'm just going to sketch a picture of what it would look like. It's going to look like this, where the magnitude is 1. To check that, you could then plug these two coordinates into the Pythagorean theorem as a and b and solve for c and see that c is indeed 1. Okay, the second question says vector v has an initial point of -4 and a terminal point of -3, -6. Okay, so the first thing we need to do is actually write the component form of this vector. Now, to write this as in component form, I'm going to take my terminal position minus my initial position. So let's see, -3 minus 1. So my horizontal direction is -4. And then -6 minus a -4. Double negative becomes positive, so that's going to be -2. So I am dealing with a vector -4, -2. Okay, now I want to write the unit vector. So if you're sketching this, we now have this in standard position, so its horizontal direction is left 4, its vertical direction is down 2, and there's our vector. Now we need to know the magnitude so we can write the unit vector, because remember the unit vector has a magnitude of 1. It's going to be very small, same direction. So let's find the magnitude by just using the Pythagorean theorem. Let me switch colors. -4 squared plus -2 squared is equal to c squared. So we have a 16 plus 4. And that's equal to c squared. So that means c, which is the magnitude, is the square root of 20, which we can then write as 2√5. So there is our magnitude. So 2√5. Now, that's the magnitude of the entire larger one. Now to find the unit vector, I'm going to erase this. Let's go back. I'm going to take the vector -4, -2, and I'm going to multiply it by 1 over the magnitude. In other words, I'm going to divide by the magnitude. So if I just divide this by the magnitude, I'm going to have -4 divided by 2√5 and -2 divided by 2√5. And I just need to rationalize those positions. So let's multiply by radical 5s and simplify that 2. So if I cancel the 2 out, that's going to give me -2 √5 And then root 5 times root 5 on the bottom is 5. And then rationalize this one. So multiply by a radical 5. And that's going to, the 2's will cancel completely. So that's going to end up being negative root 5 over 5. And what does this represent? This represents my unit vector in the same direction. So it's this little red one that has a hypotenuse of 1. Okay, so let's talk about direction. Okay, direction is just the angle, or the angle as if you're using the unit circle off of the x-axis. So it's the angle that the vector creates with the positive x-axis. So we're going to look at vector. In this case, the vector is AB. And to find this angle, we just use tangent. Why do we use tangent? Because if you have a coordinate AB, A is your x direction, B is your y direction. To find the angle, we're going to use the tangent as opposite over adjacent. So we're going to use the tangent of theta to find this angle. Now that works really well for quadrant 1, but what you're going to be finding are reference angles. So we may have to add or subtract to 180 depending on the quadrant. So I want to look at those scenarios today. So let's start with the vector -4, +4. Okay, so that's this position right here, and here's our vector from in standard position. It's coming from the origin to the point -4, 4, and we want to find the direction. So to find that direction, we're going to use tangent. So the tangent theta of our y over our x, because tangent is y over x. So we have the tangent theta of -1, or tangent theta is equal to -1. Well, you can type that in your calculator if you want. But we also know from the unit circle, when tangent is -1 in quadrant 2, this creates a 45-degree angle with the x-axis, or the reference angle is 45. That means from the x-axis to the vector itself is 135 degrees. So that is the direction of the vector. It's 135 degrees. So now let's look at a second one. Write vector W as a linear combination given this information. Okay, so again, we're going to be working with the unit circle and coordinates on the unit circle. So we need to think about 30 degrees on the unit circle. 30 degrees, what are the coordinates for that position on the unit circle? Well, that's going to be the square root of 3 is your horizontal, over 2 is your horizontal direction, and your vertical direction is just a half. Now, remember, this hypotenuse is 1. We want to have a vector with the same angle, but has a magnitude of 5. So in other words, it's 5 times as big. So we need to draw a similar triangle. We need to draw a triangle with the same angle of 30 degrees, but this hypotenuse is now 5. So what are the coordinates for this position? Well, all we're doing is multiplying the original unit circle by a factor of 5. So basically, we're taking the magnitude of 5 times this vector, root 3 over 2, 1/2. So what does that give us? Well, if we distribute the 5 in as a scalar multiple, we're going to have 5 root 3 all over 2. And then the vertical direction is 5/2. So here is our vector with a direction of 30 degrees and a magnitude of 5. Okay, let's look in the next one. Find the direction of theta if we have the vector I plus 7j. Now, we need to recognize what form this vector is in. This is in what we call a linear combination. For simplicity, I'm going to go ahead and write it in component form. So there's a 1 here. We don't write it, but it's 1. And then we have a 7 for the vertical direction. So here's our linear combination form, and here's our component form. Now what we need to do is we need to take this vector and find direction. So we're going to take the tangent of our angle theta, and that's equal, tangent's always sine over cosine or y over x, so 7 over 1. Now this one is not on the unit circle, so let's grab our calculators and calculate this. Sorry, let's get our calculator open here. So we need to take, how do we type this in the calculator? Well, we need the angle, so we're going to have to do the inverse tangent of 7, or 7 over 1. We don't need to put the 1 in, so it's a whole number. So let's take our inverse tangent of 7. And that's 81.9. So this is 81.9 degrees. Now, we need to think these coordinates are both positive, +1 and +7. So that means this vector lies in quadrant 1. And what we just found was the reference angle of 81.9. So we don't have to add or subtract that to 90 or 180 or anything because we're already in quadrant 1. Now let's look at one that's not in quadrant 1. We're going to take the vector. Let me slide this down just a little bit so you can see it. Okay. Find the direction theta if vector v is 2i minus 3j. 2i minus 3j is the linear combination. Now let's write it in component form. So we're looking at 2, -3. So as far as a quadrant, what quadrant's that going to be in? It's going to be in quadrant 4. So let's just sketch this out. So we're going to look for that direction. Now, when we calculate this with tangent, it's going to give us the reference angle. We don't want the reference angle. We want to know this angle to give a direction. So we're going to use our unit circle concept just to take 360 and subtract the reference angle to get the actual angle that we're going to find. Okay, so let's find the reference angle. So tangent of theta is equal to -3 over 2, which would be, right, 2 and -3 when we draw a triangle. So we're going to take the inverse tangent of -3/2 and grab your calculator. So second tan of -3 divided by 2. And that gives us -56.3. So the angle, the reference angle is 56.3. That is the reference angle. We know tangent is negative in quadrant 4 and negative in quadrant 2. So that's why it's negative. But we actually want this angle. So what do we need to do? We need to take 360 and we need to subtract that reference angle of 56.3. And that's going to give us our direction. So let's take 360 minus 56.3, and that gives us 303.7. So the direction of the vector is 303.7 degrees. Okay, so that gives you an idea of just directions. Now I want to go back and work a little bit more with a unit vector and think about the unit vector's positions for each of our common angles in a unit circle. So write a unit vector with the following angles in component form. Well, let's think about this unit circle. We know at 45 degrees, the values on the unit circle are root 2 over 2 and root 2 over 2. So that means our unit vector with a hypotenuse of 1 is simply those two coordinates. So as a vector, we would write the vector root 2 over 2, root 2 over 2. And that's true for all of them, okay? So let's look at a unit vector for 60 degrees. Okay, 60 degrees, that's still in quadrant 1. That's a short in the x direction, a long in the short direction. So that's going to be a 1/2 and a root 3 all over 2. And that is a vector. So let's write the vector symbols. Okay, what do we know about 90? 90 is here. What are the coordinates for that? 0 and 1 are the coordinates for this position. So to the right, the vector is going to be the vector 0, 1. Well, isn't that just the j vector as a linear combination? That's just the unit 1j vector. Okay, and then 135. Okay, that one's in quadrant 2. It's right here, and we know it's a negative square root of 2 over 2 and a positive square root of 2 over 2. And so the vector, the unit vector at 135 degrees is negative square root of 2 over 2 and root positive square root of 2 over 2 as a vector. Okay, so just to get some sense of the unit circle and a unit vector on that circle. Now, using that knowledge, we're going to now write vectors that have the same angles on the unit circle but are larger, are not shrunk down to that magnitude of 1, but are larger. And how would we write that? So let's take the 45-degree angle. We just saw that the vector for that position on the unit circle is root 2 over 2 and root 2 over 2. Now all we're going to do is take that vector and multiply by the new magnitude because we're making it 12 times larger. So if we distribute using scalar multiplication that 12 in, that's just going to give us the vector 6 root 2 and 6 root 2. And there we go. Whoops, that's not an ordered pair, it's a vector. Okay, and there's our answer for that first one. So let's look at 150 with a magnitude of 8. Well, let's write the vector at 150, and that's negative square root of 3 over 2, positive 1/2, and that has a magnitude of 1, but we don't want 1, so we're going to multiply it by magnitude of 8. Multiply by 8, so distribute it in because it's a scalar, and that gives us negative 4 root 3 all over 4. And there is that vector. Okay, how about 240? Well, 240 is that last position right before we get to the negative y direction. So that's going to give us what? Negative 1/2 as a vector and negative root 3 over 2. That is the unit vector, or the position on the unit circle, which is a unit vector. Okay, and we're going to multiply it by a magnitude of 6. So let's multiply by the scalar 6, and that's going to give me the vector negative 3 and negative 3 root 3. And there's the answer to that third one. So you can use your unit circle to find larger vectors. So write the vector with a magnitude of 8 in the direction of 30 degrees. Let's try one more of these. Magnitude times 30 degrees, which is root 3 over 2 and 1/2. And that one's just going to give us 4 root 3 and 4. Very simple. So let's look at it visually. You've got a unit vector that looks like this. That's 30 degrees. The hypotenuse is 1. This one is 8 times larger. 1, 2, 3, 4, 5, 6, 7, 8. Same position. So what are these distances? And that distance is 4 root 3. And that distance is 4. So just giving you a visual. And this red vector right here has a magnitude of 8 with an angle of 30 degrees. And then the last one, we're going to take a magnitude of 14 times 135. Well, we just did one at 135, and that's one of our 45-degree angles, but in quadrant 2. So let's multiply it. And that's very simply the vector -7 root 2 and +7 root 2. Okay, so I think you got the hang of the ones on the unit circle. Now, let's look at some that are not on the unit. Whoops, I got a typo there. Not on the unit circle. Okay, let's look at this one. This one has an angle of 70 degrees, but we want the magnitude. Whenever you have the double lines, that represents magnitude. It has a magnitude of 10, so a length of 10. Okay, so what's it going to look like? Let's go back and talk about these for a second. Don't we know that the x direction is always the cosine, and the y value is always the vertical, which is our sine? Okay, so cosine is always first and sine is always second. So what we're going to do for the ones that are not on the unit circle, we're going to write those as sines and cosines. So this vector is the unit vector is, whoops, not sine, but it is cosine of 70. That would give us this horizontal direction. The vertical direction would come from the sine of 70. And that would be the unit vector. But what have we been doing? We've been taking the unit vectors and multiplying by 10. So we're going to take 10 times each one of these. So guess what? This is going to be, the final vector is 10 cosine 70 and 10 times sine of 70. So you're going to have to get your calculator out and just multiply those out. So let's go back to our calculator. And let's see, I'll clear some stuff out. We're going to do 10 times the cosine of 70. So we can see what that distance is. That's 3.42. So let's write that as 3.42, and 2 decimal places is plenty. Okay, and the y direction, let's multiply 10 times sine of 70. So let's take 10 times sine of 70, and that'll give us the vertical direction. And that's 9.40? 9.40. And that would be the vector that has a magnitude of 10, whoops, but an angle of 70. Okay, so let's try another one of those. Okay, this one, we're going to take, this one has a magnitude of 32. So it's 32 times as large as the unit circle. Okay, it's 32 times that hypotenuse. So very simply, we're going to take the magnitude of 32 and we're going to multiply it times, well, our horizontal direction is cosine of the angle. Well, the angle we have to use is the angle from this x-axis. We need to use this 140, not the reference angle of 40, but the actual direction of the vector. And that's why direction is so important, because once we're finding that direction, you can then find the length of the vectors. Okay, and then we're going to take the sine of 140 for the vertical. So let's grab our calculators and distribute that in. 32 times cosine of 140. And that's going to give us negative 24.51. So negative 24.51. Well, negative makes sense because we are going in the second quadrant with a 120-degree angle, so the x-coordinate should be negative. but we know the y-coordinate should be positive, so let's check it. We're taking this time 32 times the sine of 140. And that gives us 20.6, I'm sorry, 20.57. So 20.57. And that is the vector that has a magnitude of 32 and a direction of 140. Now, how could I check that? I can actually use the Pythagorean theorem with the negative 24.51 and the vertical direction of 20.57. I can use the Pythagorean theorem and see if I get 32. So let's just do a quick check. So I'm going to take the quantity, negative 24, what was that, 0.51. I'm going to leave it like this so I can see it. And I'm going to square that, and I'm going to add 20.57. I'm going to square that. That's going to give me c squared. So let's take the square root of that answer. And 31.99, which is 32, rounds up to 32 degrees, or 32. So the magnitude is indeed 32. Now, the only difference on this one is you're not given the magnitude, it's just drawn on there. But you would just take 4.5, which is the magnitude, times the cosine of 310, and then the sine of 310. So work that out and see what you get. And that should be what? A positive and then a negative vector because it's in quadrant 4. Okay, so we have 3 different forms of vectors, and I just wanted to review those. The first form is what we call component form. The second form is a linear combination, and then this third form is the direction and the magnitude form. Okay, so this is the new form we're working with today. So find the magnitude and the direction from each of the forms. Well, the magnitude, if you can sketch it if you need to. This would be over 7 up 24, right? And then our direction is, well, it's pretty big angle. It's going to be close to 90. Not quite, something probably in the 80s, 70s. Pretty large angle. This is 7 and this is 24. So we're just going to take the tangent of the angle theta is equal to sine over cosine, or y over x. Now to find that, I hit the wrong thing. Let's bring our calculator up. Let's do the inverse tangent of 24/7. And that will give us our angle. And that's 73.74. 73.74. So it is a pretty large angle. Okay, and that's how we would find the direction. Now to find the magnitude. Magnitude is the length. So let's just use the Pythagorean theorem to find the hypotenuse, which is that length of the vector. So this is going to be the vector's magnitude, right, squared. So working this out, we're going to get 7 squared plus 24 squared, and take the square root of that, and that is going to give us 25. I should recognize that. Why didn't I recognize that? Okay, that's one of our triples we've learned this year. So the magnitude is 25. Okay, so now let's look at the second one. Rather than erase it, I'm just gonna make it small for now. Slide it to the side. Okay, now the second one, remember this one's not in quadrant 1. This one has a positive 5 and a negative 7. 5, 6, 7, something like that. I'm just sketching these so you can get a sense of what they look like. Okay, there's my vector. Positive 5 is this direction, negative 7 is this direction for my triangle. I'm looking for the reference angle theta first. But because this is in quadrant 4, I have to give my direction as this larger angle. So we're going to have to subtract the reference angle from 360. So to find the angle, the reference angle, let's take the tangent of theta, and that's what, negative 7/5. So grab your calculator and do the inverse tangent of, whoops, I did it again, negative 7/5. And that gives us the angle. Oh, what did I do wrong? Put the wrong negative there. There we go. Negative 54 point, I'm going to round that off to 5. So negative 54.5 is the angle measure. And again, tangent in quadrant 4 is going to be negative, but we're going to subtract that from 360 to get the angle, to get the direction. So let's go back to our calculators. 360 minus 54.5. And that gives us 305.5. So 305.5 would be the direction. Okay? Now we just need magnitude. So let's find the magnitude. Again, we use the Pythagorean theorem. So 5 squared plus negative 7 squared is equal to the magnitude squared. So that's 25 plus 49. And that's going to give us what? 74. Right? Yeah. So the magnitude squared is 74. So it's the square root of 74, and that is the magnitude of this vector. Okay, so we've worked with both of those, both of the forms that we've learned, component form and then a linear combination. Now let's look at the newest form, okay? This one's really easy to find direction and magnitude, because what do we know? The magnitude is simply the scalar multiple. So on this one, our magnitude is just 6. And then what is our direction? Our direction is given as the sine and the cosine. So the direction is just 32 degrees. Now that's in quadrant 1, so it's easy, it's positive, it's just right there in the first quadrant. Now, this angle can go up to 360 degrees. So it would just change which quadrant it's in. But it's very, very simple to find the magnitude and the direction of this vector. And that's where we're going to stop today. So I hope this video was helpful on learning magnitude and direction. We've looked at vectors in different forms, component form, linear combination, and then with the magnitude and the direction for those that are not on the unit circle. And then remember, the ones that are on the unit circle, you can very simply take the position on the unit circle and just multiply it by that magnitude. So I hope this video was helpful, and you can work on the next lesson.